Welcome to Base 10 Logarithms. So logarithms, or logs, have both a base and an operand. So the base is then written in subscript down here, or sometimes it's just left off entirely. So if you just see log of some number, in this case 100, if we don't have a base written there, then it's understood that we have a log with a base of 10. Because in our number system, we go by tens. So we have 10 digits, right? We go from 0 to 9, and then we go up to 10. And in that case, then, going from 9 to 10 requires us to write now a second digit. So now we have a 1 in our second digit's place, and then a 0 in our ones place, right? So we have a 1 in the tens place and a 0 in the ones place. So again, we have a base and an operand. So log of base 10 of 100, well, remember that 100 can be written as 10 times 10. So log base 10 of 100 is then 2. We're basically asking the question, how many tens do we have multiplied together in the number in there, in our operand? So log base 10 of 100 is then 2. And so we can continue this if we have log base 10. Now I'm not going to write the 10 as the base of 1,000. That then gives us 3 because we need 3 tens. So log of 10,000 would then give us 4, and so on. So let's look at a case where we have a logarithm with a different base. In this case, we'll have log base 2. Now log base 2 is going to be something that's common for something like computers, because they have a binary system where they're only counting basically 0 and 1, whereas in our number system, most of the time we're displaying numbers in a base of 10. So we have digits that go up through 9, 0 through 9. So that's 10 digits, because of course the 0 counts as 1. So log base 2 of 16 is basically asking how many 2's do we have to multiply together to give us 16? Well, remember that 16 is 2 raised to the 4th. So log base 2 of 16 is then log of base 2 of 2 raised to the 4th power, which is then 4. So now let's discuss logarithms and significant figures. The first digit in the result of a logarithm does not count for sig figs. Now in general, we want to report our answers for logs to the hundredths place. So if we have, say, log of 100.0, in this case we have 4 sig figs, and in this case then we're going to report our answer to, we have, if this is log base 10, we have a value of 2, and then we have to keep our sig figs in there, and we need 4 sig figs, and again that first digit, the 2 here, does not count. So in this case we would have to report 4 zeros in there. Now again, I've said here that in general we want to report our answers for logs to the hundredths place. So in this case it would be acceptable to write this as 2.00. As long as you remember that this 2 does not count for sig figs. So in this case we don't have 3 sig figs in our answer. We only have 2 because it's just these 2 digits, the 2 zeros there, that count as sig figs. This 2 here is not a significant figure because essentially our 100 here could be written as 1 times 10 to the 2, and that 2 in the 10 to the 2 is this 2 here. So suppose we want to know what is the pH of a solution with the hydrogen ion concentration of 1.0 times 10 to the minus 7. Well, we need to know how to calculate pH, and pH is defined as minus log base 10 of the hydrogen ion concentration. So these little brackets here, these square brackets on either side of the hydrogen ion there, mean concentration, and so this is going to be in molarity. So unwritten over here is a unit of molar on our hydrogen ion concentration. So to calculate our pH, we need to take minus log base 10 of our hydrogen ion concentration. So minus log base 10. Remember, if we don't have a base written, it's base 10. So minus log of 1.0 times 10 to the minus 7. And again, we have unspoken units there of molar. Now when we take the logarithm here, those units go away. Right? So basically the answer to any logarithm has no units to it. So our pH has no unit on it. So we have minus log base 10 of 1.0 times 10 to the minus 7. Well, the log of 1 times 10 to the minus 7 is going to be minus 7. So we have minus from a carryover of this negative sign here. And then the answer to our log term there is going to be minus 7. And I'm going to report this to 2 sig figs, because again, here, 1.0 times 10 to the minus 7, we have 2 sig figs, the 1 and the 0. And so this first digit is basically our 1 up there, and the second digit here is our 0. And so now we have negative times a negative 7, and that means that our pH is equal to plus 7.00. So we've talked about how to take the log or logarithm of some number, and now we need to figure out how to undo that. That is, we need to take the anti-log or the inverse log. And this is how we convert from logs to numbers. So in this case here, we have log base 10 of x equals 4, and if we want to solve that for x, we need to get rid of this logarithm term. So to do this, we need to take the anti-log, and that then involves taking the base of our exponent, which in this case is 10, and raising that base to the power of the stuff on either side of our equation. So we're going to take 10 and raise that to the power of log base 10 of x, and that's then going to be equal to 10 raised to the power of the other side of the equation, which was just 4. So 10 to the 4 is equal to 10 raised to the log of x. And now these two operations, this 10 raised to the power of and the logarithm term, cancel out because we have a log and we have an anti-log, that's the 10 raised to the power of. And so now on the left side we simply have x, and on the right side we have the same 10 to the 4. So if we have an x of 10 to the 4 and we take the log base 10 of that, we will have a value of 4. And again, that was then what we had on the other side of our equation up there. So you might be asking yourself, well, when would we ever have to take the anti-log? Well, in a case like this. If we want to know what is the hydrogen ion concentration for a solution with a pH of 5.0, remember that before we had the hydrogen ion concentration and we solved for the pH. Well, now we're going backwards. So before, when we had the hydrogen ion concentration and we went to the pH, we had to take the logarithm. Now, if we have the pH and we're going back to the hydrogen ion concentration, now we have to take the anti-log. So remember that pH was equal to minus log base 10 of the hydrogen ion concentration. So if we want to solve this equation for the hydrogen ion concentration, that means we need to get rid of this log term. So now we know that the pH is 5.0, so we can plug in 5.0 is equal to minus log base 10 of the hydrogen ion concentration. And now we want to solve for that guy, the hydrogen ion concentration. Well, first let's move this negative sign to the other side. So now we have minus 5.0 equals log of the hydrogen ion concentration. And now we need to get rid of the log term. So again, we're going to take 10 and raise it. Right? 10, again, was our base here on our logarithm. So we're going to take 10 and raise it to the power of each side. So 10 to the negative 5.0 is equal to 10 to the log of the hydrogen ion concentration. And then the right side here, this 10 to the log, becomes just the hydrogen ion concentration, because we have our logarithm and our anti-log. And then the left side was then 10 to the minus 5.0, which then means that this is equal to 1 times 10 to the negative 5 molar. So our hydrogen ion concentration here is equal to 1 times 10 to the minus 5 molar. So note, here I've written only a single sig fig because up here in our 10 to the negative 5.0, the negative 5 there does not count as a sig fig. The 0 here does count as a sig fig. Remember, the negative 5 is just a placeholder. That 0 is not a placeholder. This one, the 0, is our sig fig, but we only have 1 there, so here we only have 1 sig fig.